All right, well, today we're going to do Chapter 6. Chapter 6, unfortunately, has a name with the word quantitative in it, which makes it sound difficult. My goodness. Okay. Has quantitative in it, makes it sound very difficult, but actually it's going to be fairly intuitive, I believe. I hope. Any questions before we get started? Well, today we're going to talk about stoichiometry. We're going to do calculations involving stoichiometry, but it all begins with things that we've seen many times. Chemical change can be described by an equation. We have reactants, we have products, and a reaction arrow. We said the arrow has the same properties as an equal sign, same numbers and types of atoms on both sides, and of course, the same mass. In order to achieve that, we put in coefficients. These coefficients will describe what we call the stoichiometry. Stoichiometry is simply the coefficients expressed in terms of moles. Step one is always to balance your equation. If we look at this equation, we have 2 bromines, we have 3 bromines. Let's fix that, make it even. This now gives us 6 bromines here, only 2 there. And we have 2 aluminums, so we need a 2 in front. If you do your simple inspection, 2 aluminum, 6 bromines on each side. Now, we can also express that in terms of what we call the theoretical yield. That is, we're going to express the coefficients in terms of molar quantities. If we had 2 moles of aluminum and we reacted it with, quote, excess bromine, so that's all the bromine in the world you need, we will get 2 moles of product. That is a theoretical yield. Why do we use excess bromine? Well, if you remember our little video clip, once we get the reaction started, lots of toxic low bromine fumes boil out the top, and they're gone. So trying to weigh out exactly the amount of bromine you need is difficult. We always just put in too much. All right, let's go ahead and look at a different reaction now. This is the organic alcohol ethanol. It reacts with oxygen in the room, and it burns, undergoes oxidation. When it does, it gives CO2 and water. First thing we do is check to make sure we're balanced. 2 carbons, 6, 7 oxygens. 1, 2, 3, 7 oxygens. Yeah, I think we're okay. 6 hydrogens, yeah. Okay. We want to know how many moles of CO2 we're going to get if we had 2.5 moles of ethanol. All right, let's think about this in the problem-solving algorithm that we know. Moles of ethanol, which you're trying to find, 2.5 moles of, CO2, 2.5 moles of ethanol, or what we have. That's our given. According to the equation, the link between CO2 and ethanol, so this and this, is 2 to 1. Now, ethanol is going to be our given, so we're going to want a ratio with that in the denominator. Something like this will work. 2 CO2s for every ethanol. 2 CO2s for every ethanol. Now, we simply start with our given, 2.5 moles of ethanol, Here's our ratio. We'll call this a known ratio because it's from the equation, and this is what we're trying to find. First comes the given. Going to multiply that by a ratio. Moles of ethanol will cancel. That's why we put it in the denominator. 2.5 times 2 divided by 1, 5 moles of CO2. Can't get much simpler than that, can you? All right. This is one way to do it. There's another way to do this that I think is actually a little simpler, a little faster. It's using two ratios. Now, one ratio is the one that we just used, 2 CO2 to every ethanol. The other is an unknown ratio, and that's going to be what we're trying to find over the given. So let's see how this works. The ratio from our balanced equation is 2 CO2s for every ethanol. We always set this up with our given in the denominator. What we're trying to find is going to be X. So moles of CO2 is X. Moles of ethanol is our given. We have, looking for moles of CO2, we have 2.5 moles of ethanol. So we have a known ratio from the equation and an unknown ratio from the problem. The reason I think this is simpler, once you set up these ratios, all you have to do is 2.5 times 2 divided by 1 on your calculator. Don't have to write anything out. Here's the calculation. Moles of ethanol cancel. 2.5 times 2 divided by 1. Nice simple strokes. If you want to do it the other way, this is what we're actually doing. 2.5 times 2 divided by 1. If this looks familiar, this is given. This is our ratio from the other way. And that's what we're trying to find. So it's exactly the same. You just don't have to write this out a second time. Any questions? Well, that was so simple. Let's do another one. Calcium reacts with HCl. We did this in lab to give calcium chloride and hydrogen gas. We're looking for how many moles of HCl, and we have 3.25 moles of calcium. So they're both reactants, but that works. That's fine. We look to see how we balanced. 1 calcium, 2 chlorines, 2 hydrogens. Yep, we're balanced. It's good. So, according to this equation, 1 calcium requires 2 HCl's. So that's going to be our ratio. Again, calcium is in our denominator because it's the given. So let's just set up a ratio. This is 2 moles of HCl for every calcium. Now, our unknown ratio, moles of HCl is going to be X. Moles of calcium is the given. X over given gives us this. So on your calculator, 3.25 times 2 divided by 1, that's all you have to do. We cancel it, that way we know we've set it up right. If you want to do it the other way, the intermediate equation would look like this. Once again, this is our given, this is our ratio, and that's what we're trying to find. 6.5 is what we get. Now, this next problem I have to apologize for a little bit. One year, I was feeling a touch crabby when I wrote the test, and I put this as a 3-part question on the exam. Part 1, balance this equation. Well, we have 2 carbons, we have 1 carbon. We fix that. We have 6 hydrogens, we have 2 hydrogens. We can fix that. Where do we stand with oxygens? We have 3, 4, 5, 6, 7. Now, oxygen, unfortunately, comes in pairs, doesn't it? So to get 7 oxygen atoms here, we would need 3.5. Well, we typically don't like using fractional coefficients, do we? It is actually technically correct, but convention is only integers. If you're doing an equation like this, and you find yourself with something that's a non-integer, first thing to try is just double everything. So instead of 1 ethane, we have 2, we have 7 oxygens, 4 CO2s, and 6 waters. And that works. So that was part 1 of the exam, of the question. Part 2, according to the problem here, we have a reaction, 7 moles of oxygen gives 4 moles of CO2. So we're linking oxygen and CO2 is going to be our given. So we'll put that in our denominator, and there we are. Now, our unknowns. X is going to be moles of molecular oxygen. And our given is 1.7 moles of CO2. So we set these up like that. On your calculator, 1.7 times 7 divided by 4. Moles of CO2 cancel, so that's good. Simple math. Again, this is the long way. 1.7 times 7 divided by 4. And we wind up with 2.975 moles of oxygen. So what was the third part of this question? We have 3 significant figures here, don't we? We have 4 from our calculator. Round this number. We have a rule for that, don't we? If your number ends in exactly 5, what do? You round even, not always up, even. This goes 298. Now the good news is, I'm not feeling crabby this semester, so you won't see anything that's complicated. Okay? Good. Let's do yet another one. This is chloroacetic acid control, reacting with oxygen to give carbon monoxide, water, and HCl. we're looking for moles of oxygen. We have excess chloroacetic acid, and we have 0.2645 moles of carbon monoxide. So, according to our equation, 1 mole of O2 gives 4 moles of CO. So 1 to 4 is our ratio. CO is going to be our given, so that goes in the bottom. Our unknown ratio, we're looking for moles of oxygen, that's X. Moles of carbon monoxide is the given. And we simply multiply 0.2645 times 1 divided by 4. Again, you don't have to write out anything, but you could. Moles of CO will cancel, and this is your calculator answer. Now, one more time. 4 significant figures. Calculator gave us 5. What do? We round even. In this case, we round down. That's why the rule works. Half the time up, half the time down. Any questions? Well, there are a couple tutorials that accompany this chapter. Molar stoichiometry, it's called. Here's our reference equation. Here's our known ratio. Here's the unknown ratio, just to remind you. Excuse me, that's my son who forgot I'm teaching. So, we want to find the number of moles of sodium hydrogen carbonate. That's that. Our given is going to be moles of sodium carbonate. It's that. So, our ratio here, sodium hydrogen carbonate to sodium carbonate, with sodium carbonate in the denominator, is 2 to 1. 2 to 1. Here's our unknown ratio. We're trying to find hydrogen carbonate. We are given this guy. Once again, 2 times 0.82 divided by 1, 1.643. Sounds complicated because it's called stoichiometry, but really it's not that bad, is it? It gets worse, but it's not that bad yet. Let's do one more. We're linking chloroethane and chlorine. There are 4 chloroethanes and 2 chlorines. Our ratio could be 2 to 1 or 2 to 4. Doesn't matter, same math. Our given is going to be chlorine, so that's going to be in our denominator. 2 to 1 is our ratio. Here's our given. Here's the given. Here's what we're trying to find. 0.9922 times 2 divided by 1. 1.984. Any questions so far? These are what we refer to as mole problems, because we're talking only in units of moles. Everything is given in moles. But if you're in lab, you don't weigh anything in moles, do you? You weigh it in grams. Therefore, we need an approach to do mole-gram problems. So, moles and mass. Potassium chlorate gives KCl and oxygen. It's our gummy bear reaction, remember? we're looking for how many grams of potassium chlorate we need to get 2.25 moles of oxygen atoms, not molecules, atoms. So our ratio here is going to be 2 to 6. 2 moles of potassium chlorate, 6 moles of oxygen atoms. So let's set up our known ratio, oxygen in our denominator. And our unknown ratio, we simply have X right here, and we have given right here. Again, on your calculator, 2.25 times 2 divided by 6 gives us 0.75 moles of potassium chlorate. So if this was a mole-mole problem, we'd be done, wouldn't we? But it's not. It's a mole mass problem. So our question now is, how many grams of potassium chlorate do you weigh out if you want 0.75 moles? Okay, what you do is you remember the one thing that we always remember. Mass divided by molar mass is moles, right? We're looking for mass. That's molar mass multiplied by moles. So, we know the number of moles. We need to calculate molar mass here. On the exam, I actually gave it. 1.225. Number of moles multiplied by this would give us our mass. There's our mass. Here's our molar mass. And we're talking about 92 grams. So what you would do is simply go in the little room, weigh out 92 grams of potassium chlorate, and that will give you 2.25 moles of oxygen atoms. That makes sense, right? Well, the other variation in all of this is a mass-mass problem. Again, this is even closer to reality because you weigh everything out, don't you? So, here we have zinc sulfide reacting to give zinc oxide. Reacts with oxygen, we get SO2. Again, the equation is nicely balanced. We're looking for a mass of zinc oxide, that's this, and we have 25 grams of zinc sulfide. So this is going to be X, that's going to be given. We look at our equation, we're linking zinc sulfide and zinc oxide. It's 2 to 2 or 1 to 1. So we'll just leave it 1 to 1. 1 mole of zinc sulfide, 1 mole of zinc oxide. And we write it down. Now, the unknown ratio, grams of zinc oxide, are given as grams of zinc sulfide. And we stick those in after we calculate the molar masses. Oh, sorry, I forgot a step, didn't I? So here's our mole ratio. But we want everything in terms of mass, don't we? So let's convert our mole ratio to masses. And for that, we need the 2 molar masses. 1 mole of zinc sulfide is 97 grams. 1 mole of zinc oxide is 81 grams. Simply substitute those in. Now we do our unknown ratio. Zinc oxide is what we're looking for. Going to be on the bottom. Zinc sulfide is on the top. That's X. That's given, and that's what we write. Now we look at this and say, oops, when I set this up I did it wrong, didn't I? But that's okay, because the math is very simple. If you set things up upside down, just flip them both over. Totally legal. If it doesn't work out, flip it upside down. Now it's 25 times 81 divided by 97. Zinc sulfide will cancel nicely. And we're talking about 21 grams. So, doing mass isn't difficult either. The only trick is to take the mole ratio from the stoichiometry, 1 to 1 in this case, and substitute in molar masses. That's all you have to do. All right, one more variation. And this is mass ratios. We have to use this if our stoichiometry is not 1 to 1. So in this equation, we have fluorine reacting with water to give HF and oxygen. We're balanced. Our ratio here for water and HF, there's water, there's HF, is 2 to 4 or 1 to 2. But it's not 1 to 1, is it? So instead of just writing down the simple mass ratio, like we did in the previous problem, we have to write down one corrected for the stoichiometry. 2 moles of water, 4 moles of HF. Bless you. 2 moles of water, 4 moles of HF. Now, every mole of water is going to weigh 18. Every mole of HF will weigh 20. So we simply multiply this. There's our 18. There's our 20. Lots of stuff cancels. 2 times 18 divided by 4 divided by 20. 36 over 80. Simple way to think about a mole or a mass ratio is this. If we had 36 grams of water, this tells us we would get 80 grams of HF. 36 grams of water gives us 80 grams of HF. Okay. So, once again, the mass ratio, stoichiometric coefficient, that's our 2 and our 4, multiplied by molar mass, 18 and 20. So, to finish up the problem, this is X, grams of water is on top, that's good. Grams of HF is our given. Simply set that up. 62 times 36 divided by 80, 21 grams of water. Nice and straightforward, right? Same sort of problems, you just have to decide, are you doing mole-mole, mole-mass, mass-mass, or mass-mass where we need to do a mass ratio. Well, of course, there's a tutorial. There's a definition of mass ratio to help you out. Here we have cobalt-2 reacting with oxygen to give cobalt-3. We want to look at the link between cobalt-2 and cobalt-3. Cobalt-3 is our given. So, cobalt-2, we have 4. Cobalt-3, we have 2. That's a 2-to-1 ratio. So our mole ratio is going to be something like this. 4 moles of cobalt-2, 2 moles of cobalt-3. Now we're going to multiply those by their molar masses. 4 times 75, 2 times 166. This is our mass ratio. You don't have to go ahead and calculate it out, but of course you could. You could also just look at this and say, hey, it's a ratio. I know what's given. By George, I can just do it this way. Given times ratio. 40 times 4 times 75 divided by 2 divided by 166. 37 grams. Any question? All right, well, next is the concept of limiting reactants. Now, limiting reactants in general is a general chemistry exercise. It's not difficult. You do the exact same mole calculations we've just done, except you do it twice. So it's tedious. You do everything twice. Decide which one gives the smallest theoretical yield, and we call that the limiting reactant, because it limits how much stuff you make. We're not going to do real limiting reactants here. We're going to do just the concept, okay? So just the concept. You can wait for general chemistry for the torture. But winter's coming. Let's pretend you have 4 children, right? I know it's a nightmare sometimes. I had 4 children. You go in the closet. It's time to get gloves out, because it's going to be cold, right? So you reach in your stack. You see you have 4 left-handed, 3 rights. So you take kid number 1, and a pair. Kid number 2, it's a pair. Kid number 3, it's a pair. Kid number 4 gets 1. That's because we have more left-handeds than we do rights. So the right-handed limit how many pairs you have. Poor 4th child, right? Right. If you have 4 kids, you understand that one. All hand-me-downs and leftovers. Okay. We're not going to do gloves. When I say a concept question, it's something like this. If we take fluorine, react it with chlorine, we can get chlorine trifluoride. All right? Let's pretend that we have 3 chlorines and 1, 2, 3, 4, 5, 6 fluorines. Okay? In order to make ClF3, 2 atoms of chlorine require 6 atoms of fluorine. So in terms of concept, let's take and remove 1 chlorine and 3 F2s. That's 6 atoms. That gives us 2 moles of product. We can do this again. Take a chlorine, take 6 fluorine atoms, make 2 more moles. And what are we left with? chlorine. Who was limiting? Fluorine was limiting. Chlorine is left over, so it's success. So I've used this basic approach many times now for this type of problem, just varying the amount of things that we have. So make sure you understand the principle. When you're done with the reaction, whatever's left over is in excess. Any questions? All right, the last part of this chapter is on yields. We said when we define the stoichiometry of the reaction, we define the theoretical yield. According to our equation, 3 moles of bromine react with excess aluminum. You could do this either way, to form 2 moles of aluminum bromide. Either one could be in excess, doesn't matter. It's just one's left over. Okay, so this is our theoretical yield. The theoretical yield is 2 moles of aluminum bromide. Simple. Sadly, though, it doesn't always work that way. When you're talking about a chemical reaction, the physical description of it uses what's known as a potential energy surface. The higher you go up on the surface, the more energy you're using. Ideally, we're starting here with reactants at slightly different energy levels. They will react, go over the lowest possible pump, lowest energy pathway, and give us product. Think of it this way. This is a mountain pass, right? Let's pretend that we're all sitting here and we say, okay, well, we got to get over here. How do we do it? Virtually everybody in the room is going to say, let's start here, let's go down the valley, and we're there. Virtually everybody will do that. But I can assure you that sitting among you is someone that's going to say, I don't want to do that. I'm going to go up here and play in the silt. So instead of getting a quantitative yield here, we get less. These are called alternate pathways. Less than theoretical yield can also occur if you do something in lab. Let's say we're making a little powder of whatever, and you're walking towards the balance room to weigh it, and somebody sneezes, and it goes everywhere. Sloppy lab work or alternate pathways. Nonetheless, what you expect to get what is a yield. Theoretical yield is what we calculate. Actual yield is what's left after somebody sneezes. Percentage is just the ratio of the actual to theoretical multiplied by 100. Simple percentage. Well, we did gloves for limiting reactants, right? Let's do popcorn. This is 20 kernels of popcorn. If we pop this, our theoretical yield is 20 popped kernels, right? We take this, put it in our little pot, and pop it. That's about 20. Now we're going to take and dump this out. And that's what we get. I see 16 pop kernels and 4 that did not pop. Our theoretical yield was 20. Our actual yield was 60. How do we do percentage? Actual divided by theoretical times 100. This is 80% yield. Simple. Now, percentage yield problems can be difficult. The next two we're going to look at aren't. They look like they should be, but they're not. And then there's a tutorial. It's online called Percentage Yield, but it's really, really hard. It is. Never made it to Blackboard because it's really hard. So, we have 5 moles of sulfur. We're reacting them with aluminum. We should get 1.7 moles of aluminum sulfide. Okay, we should. We finish our reaction, take it in, weigh it, we only get 1.5 moles. What's the percent yield? Well, we have what we need here, don't we? This is our theoretical yield, this is the actual yield. All we have to do is take that ratio and multiply by 100. The ratio is 1.5 divided by 1.7. Calculate that, multiply it by 100. This is 88% yield. All right, one more. Nitrogen monoxide reacts with oxygen to give 2 moles of nitrogen dioxide. Okay? We start off with 10.5 grams of NO. Oxygen from the room is in excess. We wind up with 9.7 grams of NO2. What's the yield? Well, what we have to do is figure out our mole ratios here. 1 gives 1, right? So, how many moles is 10 grams of NO? And how many moles is 9.7 grams of NO2? That's your question. We can do that if we know the molar mass of NO and NO2. The molar masses for the two are, well, I have to add them up. We know that mass divided by molar mass, here's the mass. We need our molar mass, gives us moles. So there's our 2 molar masses, about 30 and about 46. So take our 10 grams of NO, divide by 30. That gives us 0.33 moles of NO. If the reaction went 100%, we would get 0.33 moles of this stuff, right? But probably it doesn't. NO2, we have 9.7 grams, it weighs 46 per mole. Simply divide 9.7 divided by 46. Do our calculation, and we get 0.21 moles. So we should get 0.33, we get 0.21, Very quickly, what's our percent yield? 0.21 divided by 0.33 times 100. Do the math. We're at 63%. Any questions? This is the tutorial that did not make it on Blackboard. Let's just look at it anyway. Maybe you can see why it didn't make it to Blackboard. We have 15.6 grams of trifluoroethane. Here's its molar mass. We have 6.6 grams of CO as a product. What's the percent yield? First of all, we have 1 giving 2. Okay? So a ratio is 1 trifluoroethane to 2 COs. We'll do a mass ratio, and then we'll calculate the theoretical yield. Our mass ratio, 2 COs for every 1 trifluoroethane. Here's its molar mass, molar mass. Multiply them. Don't want to do that. Last time it broke, remember? Ouch. I think we're in shape. All the buttons look there? Yes. So here's our ratio. 56 divided by 84 times our given, 15.6 grams. Going to cancel this guy. We have 10 grams, 10.4 of CO. This is our theoretical yield. Okay, this is the actual, that's the theoretical. Theoretical is 10.4, actual is 6.3, divide 6.3 by 10, multiply by 100, we're about 64%. So the reason I never put it up on Blackboard for 110 anyway is that there's just too many steps. It's not that complicated, it's just too many steps, and people were killing themselves trying to do this. So, not doing that one. What we have so far in our list of tutorials, though, we have 5. Today we did stoichiometry and mass ratios. Remember the deal. It's a great deal. At the end of the semester, after you complete exam 2, you must complete exam 2, even if you have 1,000 points. You must complete exam 2. If you have at least 350 points in your total, and that's the only line in Blackboard you look at. The only number you look at. Don't look at reds, greens, pinks, purples, whatever. Look at total. If you get 350 or more, you'll get an A right that moment and no final. It's a great deal. Do these tutorials, guys. That's it. Thank you. Have a good day. I'll see you Wednesday for lab. I don't.
You have access to her, but you have to.
No.
Okay.